Okay, now there's a couple other things I want to say about the sine rule. I'm not going to say them yet though. I just want to use this as my argument for why, wherever you possibly can, don't use the sine rule, right? If you have a choice, because depending on the information you've been given, you might not have to use the sine rule. What's the opposite? It's the cosine rule, right? So really quickly, let's revise this. Okay. Even though the cosine rule tends to be learnt at the same time as the sine rule because you need the same kind of knowledge to understand them, I think the cosine rule is best understood in terms of Pythagoras. You know, like Pythagoras? What does Pythagoras have to do with this? Well, the cosine rule is just Pythagoras on steroids. That's all it is. Okay? Did you realize that? Think about it. What is Pythagoras' theorem? Can someone state it for me? Okay, you would usually say, the normal way we say it is alphabetical. A squared plus B squared equals C squared. I'm going to say it in reverse, right? I'm going to say it in reverse, and you'll see why in a second. Okay, this is actually the way that the wording is said. If you remember learning the sentence that Pythagoras' theorem is, it's the square of the hypotenuse equals the sum of the squares of the short two sides. Okay, so that's Pythagoras. But it only works in right-angled triangles. The cosine rule takes Pythagoras and it modifies it to make it work in other triangles. Because of course, what does the cosine rule say? It starts exactly the same way, c squared. It keeps on going, a squared plus b squared. And then it's got an extra bit on the side here, right? Minus 2ab cos c. Now, of course, think about this, right? If you were in a right-angled triangle, Pythagoras, right? If you were in a right-angled triangle, C's the hypotenuse, right? So what's the angle that's opposite the hypotenuse? It's 90 degrees, right? It's 90 degrees, and cos 90 is 0. So this disappears. In other words, you have Pythagoras. Of course you do, right? But the idea here is like this. If you draw beneath this for me, a small right-angled triangle, just so we can illustrate this. Okay. So, this is our normal situation, right, for Pythagoras, c squared equals a squared plus b squared. But just think about what's happening as this angle here changes, okay? For starters, let's think about it like this. Here we go. Okay, excuse me. So our normal situation for Pythagoras is that this theta over here, C, capital C, is 90 degrees. Okay, so this is my cos graph. So where on my graph am I? I'm here, right? 90 degrees. Okay, 90 degrees. So you can see this, which is kind of like the adjustment factor, if you like. This guy is equal to 0, right? So when he's equal to 0, you just get Pythagoras, right? Well, let's just think about what happens when this here is angle C, right? Let's think about what happens as C changes. For instance, what if we made C smaller? What if we made it smaller, right? Now I'm just going to do this down here. Oh, that's a bit too big. That's okay. So if I made C smaller, so it's shrinking, okay? So something like this, for instance, okay? Off like that. Okay? So imagine I still had the same A, right? I've just tilted it over. I've still got the same B, okay? But my angle has gotten smaller. And so what happens to C? In this case, capital C is an acute angle, right? It's acute. So can you see I'm going this way, right? I went from 90 degrees, that was my starting point. And now I'm going this way. I'm in this little area here, okay? So if capital C is in this domain, right? Then cos C, can you see it's positive? Can you see cos C is positive? Right? So what I'm doing is I take what I had before, my hypotenuse, right? And I'm taking away something positive. That makes sense because my angle is getting smaller. So the side that's opposite it should also be getting smaller. Does that make sense? Can you see that? So as I go further and further this way, in fact, like if I made C like really small, okay, like that. Can you see I'm subtracting more and more and more? Eventually, like as I get to 0, this thing will be so big that it will cancel out the whole side, right? Well, you just get a straight line. That's the first case if capital C got little, right? What if capital C got big? What if you take the same triangle and I lean, this is A over here. If I lean it off to the side, right? Like that. I've got the same A, the same B down here. And now I have a much, much bigger angle for capital C. Like that. Okay. So now capital C is obtuse, right? Obtuse. So where on the graph am I? I'm over here, aren't I? Over here. So cos of capital C is negative. So I've got a double negative here. So you have C squared equals what the hypotenuse was equal to before, this. And then this is actually going to be, this whole red thing is going to be positive. Of course it's going to be positive because C, that side, the hypotenuse, is getting longer and longer and it's going to stretch out. Okay? So the cosine rule is just Pythagoras on steroids. It's just adjusting for what happens when you don't have a right angle. Okay? Now, you can see my graph there, right? See my graph, there's cos. Because cos doesn't have this problem, right? Cos doesn't intersect twice. Any line I draw through there, 1, 2, 3, 4, 5, 6, 7, 8, any line you like, right? It only intersects with cosine once, right? So it's not like you have another option that you're missing, another solution that the calculator is not telling you. It's always going to tell you the one and only solution that's correct. Cosine can hand obtuse angles to you where the sine rule can't. Okay? So if you have a choice, you should use the cosine rule rather than the sine rule.